This is the lecture video for the last section in Chapter 4, Section 4.4. Here we will be using all of our rules that we've learned so far, like how to work back and forth between a log expression and its equivalent exponential expression and vice versa, and how to use the properties of logs to expand and condense to help us solve exponential and log equations. So we're going to start with exponential equations. So an exponential equation is one in which we have exponents in there, but the exponent is the variable we're solving for. Now our base is going to be a number. There's actually two methods. I call this one method 1, but in my math lab they're going to say things like express each side as a power of the same base. So it's also called the same base power method. So this method says what we want to try to do is get each side to be an exponential expression where the base of that exponential expression is the same. Okay, so something real simple here. 2 to the x power equals 16. To turn this expression or equation into a power of a same base, since we have a base 2 over here, it is possible that we can change the value of 16 to a base 2 because 2 to the 4th power is 16. If we can get our equation to have both sides with the same base, then this method says we can drop that base and set our exponents equal to each other and then solve this equation for our variable. This was a simple one, so that is going to be our answer here. There's nothing to solve for x, but most of them there will be. That's the first method to solve exponential equations. The second method is to use logarithms. So use logarithms to solve. We have to use this method when we can't express both sides as the power of same base. Okay, so take the same similar example. 2 to the x power equals 7. Well, there's no way that I can change 7 to 2 to any power. So I would have to use logarithms. Okay. In this method, we want to make sure our exponential expression is alone. So if I have something added, subtracted, multiplied, divided to that exponential expression, I'm going to have to use my inverse operations to get rid of it. Then I'm going to take the log of both sides. Now, whether you use ln or log, natural log or common log, doesn't really matter. In my math lab, they're going to tell you express your answer in natural log or express your answer in common log. That will tell you which base to use. What I do is if the base is a 10, I use a common log. For everything else, I use natural logs. From there, we're going to simplify. That means to use our properties, mainly and most importantly, our power rule, and then we're going to solve the equation for the variable. So I have many examples here. I'll try to run through all of them as quickly as I can. I'm not going to tell you which method to use. We're going to figure that out on our own. My math lab, however, will tell you. Okay. Well, here in this example, I have 3 to the x power equals 81. I always want to try to see if I can use method 1 first. Okay, and I want to point out that we do always want our exponential expression to be alone, whether we're using method 1 or 2. So I've got 3 to the x power here. Is there any way that 81 can be rewritten as 3 to some power? Well, that answer is yes. 81 is equivalent to the value of 3 to the 4th power. So I can use method 1 here. Both of my bases are 3, so method 1 says I can drop that base 3 and x will equal 4. Okay, pretty basic, pretty simple one. Okay, example B, 10 to the x power equals 8,000. I forgot to mention in method 1 that it is possible where both sides of the equation could be changed to a different base. In order to do that, I would have to have a base to an exponent that would give me this value. So is there any number to a power that will give me the value of 10? 2 to no power gives me 10, 3 to no power gives me 10, 4 to no power gives me 10. So if I'm going to use method 1, since this is already a base 10, this is going to have to be changed to a base 10. And we can't do that. So we're going to have to use logs. So step 1, make sure your exponential expression is alone. It is. Step 2, take the log of both sides. That literally means just putting the word log or ln in front of both sides. You're not actually calculating anything in this step. Now I've changed this into an equation that I can solve. Last step in method 2 says to simplify and solve for the variable. Well, my variable is always going to be in the exponent position, which means I'm always going to have to use the power rule to get that down in front. Now that my exponent is a coefficient, now I can use my inverse operations to get my variable by itself. So since my variable is being multiplied by the common log of 10, I'm going to divide by the common log of 10, which the common log of 10 equals 1. So we could have just canceled that out there because 1 times x is x. However, x equals, in log form, the common log of 8,000 divided by the common log of 10. They will ask for a value of that. Okay, so we're going to have to change that. Let me find this one. Change that to an estimated value using our calculator. You should get, let me plug this in here. $3.903. I believe they're going to ask you to round to 2 decimals, so that's going to be 3.90. So you actually have 2 answers when you're using logs. You have the log expression, or express your answer in log form, and you also have the estimated value. Okay. Example C, I moved over to this page just so it's easier to show you the example. So on the left side, I have a base e to the x plus 4 power. On the right side, I also have a base e. However, my method 1 says both of my bases have to be in the numerator. This one's in the numerator, this one's in the denominator. What happens to exponents when we move an exponential term from its original spot in a fraction? Doesn't it always change the sign of the exponent? So I can move this e to the 2x power that's in the denominator. I can move it up to the numerator, and when I do that, it changes that exponent to a negative in this case. If it was negative down here and I moved it to the top, it would become positive. Now I have base e's, both in the numerator, so I can drop my base e's, and I'm solving x plus 4 equals negative 2x. Since my x's are all alone on the right, I'm going to move my x from the left over there by subtracting. So 4 equals negative 3x. And then I can divide by negative 3. So x equals the fraction negative 4/3. Remember, it doesn't matter where you put that negative. You can put it out in front of the whole fraction, or in the numerator, or in the denominator. Doesn't matter, they're all equivalent. Let's look at a couple more. This fraction here is the exponent. Okay, so I have a base 7 here. So 7 to no power, I can't change 7. Over here I have a root. Now we learned in section 4.3, and actually in sections 4.1 and 4.2 as well, that every root can be converted to an exponential expression. Square root of 7, remember we have an exponent of 1 there, square root means 2. So the square root of 7 is also the same thing as 7 to the 1/2 power. Now I've got an equation where both sides have a base 7. I can drop those base 7s, and I'm solving the equation x minus 2 over 6 equals 1/2. Now I'm trying to solve for x. I'm subtracting 2 from x. I'm also dividing by 6, so the inverse of dividing by 6 is multiplying by 6. Cancel that out. X minus 2 equals 3, and then I can add 2 to get x by itself, so x would equal 5. Okay? If you plug this back in here, you're going to get an equivalent expression. Okay? Next one down here, I've got e to the 4x minus 5 power minus 7 equals 11,243. This is the first one where before we even decide what method we're going to do, we have to do something. Remember that it doesn't matter in method 1 or method 2. I have to make sure my exponential expression is alone. Since it's not, I have to add 7 to get it by itself. So I'm solving e to the 4x minus 5 power equals 11,243. 250. Now, if e is your base in your exponential term and there isn't another e on the other side, method 2 is always going to be your way to go. Since e means natural log, I'm going to use the natural log of both sides. And then I can use my power rule. So I'm going to drop this 4x minus 5 exponent down in front. Since it's multiple terms, I'm going to put it in parentheses. And then I'm going to solve for x. Now in this example, we have a shortcut. By property, the natural log of e equals 1. So I can cancel that out in this equation because 1 times 4x minus 5 is simply 4x minus 5. So 4x minus 5 equals the natural log of 11,250. And then inverse operation says I can add 5 to both sides. I can't add these and combine them because a natural log and a number are not the same thing. And then I can divide that sum by 4. So x equals the natural log of 11,250 plus 5, and that sum is divided by 4. Now when you plug this into your calculator, I suggest doing it step by step. So I'm first going to hit the natural log of 11,250 and hit enter. Without clearing my screen, I'm going to add 5. I get 14.328, blah, blah, blah. And then I can take that answer and divide it by 4. You should get approximately to 2 decimals, 3.58. Okay, now there's going to be another example here in a minute where we also have a multiple term exponent, but because this isn't going to be a natural log of e, we're not going to be able to follow this process. This process only works when that is the natural log of e, or for example, common log of 10 would cancel as well because that equals 1. So make sure you're paying attention to all examples. And we're going to skip this top one. We've already done some like that. We're going to go ahead, actually we can skip this one too. We don't need that one. We're going to look at C. Okay, so C is an exponential equation. My exponential expression is alone on the left, but 5 to no power gives me 37,500. So I'm going to have to use logs. Since our base is 5, you could use either common log or natural log. I'm going to use natural log. That's just the way I was taught. Natural log of 5 to the 4x plus 2 power equals the natural log of 37,500. Again, I want to solve for this x because x is in the exponent. I have to drop it down in front using the power rule. And then before I can solve for x, because this is a multiplication problem here, this actually means I have to multiply. So 4x times the natural log of 5 is 4x natural log of 5. Positive 2 times the natural log of 5 is 2 natural log of 5. And now that I've completed that multiplication, now I can solve for my x, which is right here. Okay. So I need to get this term by itself, just like in any other equation, wherever my variable is, I need to get that term alone. So I need to get this whole term over here. Because I'm adding that whole term, I can subtract that whole term. So I have 4x natural log of 5 equals the natural log of 37,500 minus 2 natural log of 5. Do not evaluate these until the final answer, because if you evaluate it up here and start rounding up here, that's going to throw your answer off at the end. So leave it in log form until we get to the very end. Okay. Now again, I want to solve for x. X is being multiplied by 4 and the natural log of 5. So since they're both being multiplied, I can divide by the term 4 natural log of 5. That will get x by itself. So in log form, x equals the natural log of 37,500 minus 2 natural log of 5. And that difference is divided by the product of 4 natural log of 5. Now, plugging this into your calculator, again, it does get pretty complicated if you try to do it all at one time, so I would do it in steps. Natural log of 37,500. Enter. When I hit subtract, because this is a product, you have to put a parenthesis here. So in front of 2 natural log, it'll put a parenthesis here, 5. You have to close that and hit enter. And then I'm going to divide by the product. Again, this is a product, so put a parenthesis here, 4 natural log of 5. Put a parenthesis there, close that one, and close the product. And then hit enter. You should get approximately 1.14. Okay, now, your calculator is probably different than mine, but you have to make sure you're telling the calculator to do exactly what this says. So we have a log minus a product, so that product has to be in parentheses. That difference has to be divided by another product. So work with your calculator until you're getting that answer. Okay, I think that's plenty of examples for exponential. I know I gave you a lot of them. If you need more, ask. I'll show you some more. So let's move on to log equations. Now to me, these are the easier ones because we're actually going to turn all of these log equations into an exponential equation that's going to be pretty easy to solve. Okay, so these are the directions that my math lab, your textbook, is going to give you. I kind of want to give you a shortcut on that. Okay, remember that log base b of x equals y. Remember this rule that we could always convert a logarithm that has a log, a base, an answer, and an exponent into exponential form that looks like this. This is what we're trying to do. We're trying to get our equation using properties into this form where I can convert it into the base to the exponent equals x. I have to get my log equation into this form, then I will be able to solve it. Here's the thing, you have to check your answer because what we're actually solving is an exponential equation. It's going to be either a linear or a quadratic equation in this form. So our solutions actually come from this. We need to make sure that they do work in there. You cannot put a negative exponent in for x or a negative number in for x. That is invalid. So we need to make sure that our solutions actually work. So the check is part of our solution. Okay, so let's look at the first one. Let's go back. Look at the first one, A. Log base 2 of x minus 4 equals 3. Is this equation in this form? Yes, it is. Base 2 to the exponent of 3 equals our x value, which is x minus 4. That's a pretty simple equation. 2 cubed is 8. And if 8 equals x minus 4, then I can add 4 to both sides, and x could equal 12. Now right now, that 12 is a solution to this linear equation. I have to check it into my log and make sure that it works. So I'm going to plug 12 in for x and simplify this equation. Okay, so I get log base 2 of 8 should equal 3. Now you can do this many different ways. To me, the easiest way to do this is to turn it into exponential form. Does base 2 to the third power equal 8? Yes, it does. So that checks out. Another way you could do this is to use the change of base properties that we talked about using your calculator. Does log of 8 divided by a log of 2 equal 3? Well, plug it into your calculator and see. Maybe I plugged that in incorrectly. It does work out. For some reason my calculator might be on the wrong mode. It's not working right now. So we'll ignore that for right now while I look at it. Common log of 8 divided by common log of 3. Oh, I'm plugging in 2, sorry. That was the problem. I was plugging in 3 to my calculator and not 2. There we go. If I use the change of base property, remember you can go through common log or natural log. That is going to check out. The thing is, you can't just write it like this and assume it works. You actually have to go through the check, and sometimes that check can get difficult because you have to remember all of your rules. Okay, here's another one. This one's going to involve a couple different things. Remembering that the natural log is describing a logarithm with a base e. We also have to figure out what to do with that. We can't have a coefficient. Now we don't want to move it to the exponent position. We want to get rid of it altogether. So since it's being multiplied, we can divide. That gives me the natural log of 3x that equals 2. Okay, now remember that the natural log, I'm going to rewrite this, natural log means that we're dealing with a logarithm with a base e. Sometimes it helps to write an ln expression in this form because now we can easily see that the base e to the second power has to equal 3x. Now I'm solving for x, so I'm going to divide by 3. Remember the e isn't an exponent. It is a natural log value. Okay, we talked about that in section 1 of this lesson. So we've got e squared divided by 3. That is our answer. Now, because we have an e, we can estimate that on our calculator. Remember, the e to the exponent button is above your ln key. And if we round that, we're going to get 2.46. Now, this is our answer, but we have to check it. We're going to check it into the original problem. And I'm going to plug in the actual answer, e squared divided by 3. If I plug in the estimate, it's not going to work. So using fraction rules, I can cancel out those 3's. So I've got the natural log of e squared. By property, the natural log of e to any power of x equals x. So that means this has a value of 2, which gives me 8 equals 8, which does check out and proves that this does work. Okay. Next one here has an addition problem. We've got 2 log base x's, or log base 10s, common logs. Since they're connected by an addition sign, we know that we can change them or condense them into a product. Common log of x times x minus 3. Remember, common log means we're dealing with a base 10. Okay, so I have 10 to the first power equals the product x times x minus 3. So I need to simplify this equation before I know what type it is, and I have to know what type it is so I know what method to use to solve it. X times x minus 3 gives me x squared minus 3x, which means this is a quadratic equation. I'm not going to be able to use the square root property because of this x and x squared. So I'm going to have to use either factoring or the quadratic formula. In both of those methods, one side has to equal 0. So I'm going to subtract 10 to get the expression x squared minus 3x minus 10. And then you can decide from here, do I want to factor this to solve for x or do I want to use the quadratic formula? I'm going to factor this because it's a pretty simple factorable problem. So x squared will split up into x and x. And are there 2 numbers that will multiply to give us negative 10 but add to give us negative 3? Yes, it is negative 5 and positive 2. That will then allow me to find possible solutions for x by setting my factors equal to 0. And then I can add 5 here, so x could be 5, or x could be negative 2. Now, if there's 2 possible solutions for x, you have to check both of them. Okay, so I'm going to check them into my original equation. So I'm first going to check 5 just because that's what I found first. So the common log of 5 plus the common log of 5 minus 3, that expression has to equal 1. Well, this is a valid logarithm because it's a log of a positive number. This is also a log of a positive number. So you could check this on your calculator. We have a common log button. We could see, does common log of 5 plus the common log of 2 equal 1? You could do it that way. Or we could use our properties of logs and condense these. These are connected by a plus, so I can multiply 5 and 2 and get 10. You could stop there because that's a property. Common log of 10 by property does equal 1. Or you could change it to exponential form. Common log means base 10, and 10 to the first power does equal my answer of 10. Either of those ways will check out. So 5 is a solution. Let's check negative 2. Common log of negative 2 plus the common log of 5. Sorry, that's not a 5, that's a 2, negative 2 of negative 2 minus 3. This should equal 1. Okay, well here we're going to get this. Now I want you to check this on your calculator. Plug this in. Plug this in. For both of these logs on your own, you're going to get an error. That's because these are invalid or undefined logarithms. Common log of negative 2 doesn't exist. Okay, so if I can't do these logs on their own, I can't use any properties on logs that are undefined. So that proves that that is a not valid solution and an extraneous solution. So the only solution for x is going to be 5. Last one here we're going to do together. Same type of problem. I've got 2 logs. I need to get them into a form that I can convert them to exponential form. Since they're both log base 4s, connected by subtraction, I can condense them into 1 log base 4, but my expressions in them will form a quotient because of the quotient rule. Now I can change this into 4 to the first power equals x plus 2 over x minus 1, which means I'm solving the equation, and I'm going to put that over 1. 4 over 1 equals x plus 2 over x minus 1. Now remember, I want to solve for x. There's 2 of them here, but I can't solve for it when it's in a fraction, so I need to multiply both sides by x minus 1. That will cancel that out here. I will distribute here. So I get 4x minus 4 equals x plus 2. And now I can solve for x. I'm going to move my x's to the left, which means I need to move my numbers to the right. So 4x minus x is 3x. 2 plus 4 is 6. Divide by 3, and x could equal 2. Right now, that's to this linear equation. I need to make sure it works in my log by checking it. So I have log base 4 of 2 plus 2 minus log base 4 of 2 minus 1. So I'm trying to confirm that log base 4 of 4 minus log base 4 of 1 does in fact equal 1. Again, there's many different ways you can do this. The first way is evaluate each log separately. Log base 4 of 4 equals 1. 4 to the 0 power equals 1, so this log has a value of 0, and 1 does equal 1. It's the first way you could do it. Second way would be to condense these. Log base 4, 4 divided by 1 has to equal 1. That gives me the log of base 4 of 4 equals 1, and we can prove that 4 to the first power does equal 4. Those are the easiest ways to do that. Either way, both of them check out and prove that x equals 2 is my solution. Okay, so if you have any questions, let me know. Make sure you're checking your email, doing your homework, and staying up on all of your work. Have a good day.